Hello, in this lecture we shall talk about the comparison test for series. It's good to remember that the test we can use only for series with positive terms. So let's say we have a series with positive terms. We can compare this series to two well-known series with positive terms. We compare to the P series. The P series is this series which we studied with the integral test, and we know that this series is convergent when P is bigger than 1, and divergent when P is less or equal to 1. Another series which is familiar is the geometric series. So let's take also the geometric series with the positive terms. Let's say from 1 doesn't matter, where x will be between 0 and 1, strictly. So how do we compare? Here is one very simple example. Look at the series. N starts from 2 here to infinity, 1 over root of n minus 1. This is from the book, one of the first examples. When we look at this radical here, it's square root of n, so it's n to power 1/2. We can compare to P series, but what to do with this negative 1 here? Minus 1. We just drop it. Comparing, I shall use this sign, which will stay for similar. And this series will be similar to the series 1 over just root of n, which is 1 over n 1/2 power. Let's make a better 1/2 here. 1/2, and this series is divergent because it's a P series where P is 1/2 less than 1. So to compare, I just dropped this here. I dropped this negative 1. Later I shall explain why we can drop things like that. Here is another example. Let's look at the series n squared plus n plus 1 on top, and here we have n 4th power plus n squared. This is the general term, a sub n. N goes from 1 to infinity. Now, here we reason this way. There are different powers of n. The largest power is n 4th power. It will dominate n squared. And from top and bottom, I shall drop the terms with smaller powers. I shall keep just the terms with largest powers. So here on the top, I keep n squared. And below, I keep n 4th power. And all the others I just cross out. This series will be similar to the series n squared on top and 4th power below. After reducing, we have 1 over n squared. Sorry about this square. 1 over n squared, which is convergent. It's a P series where P is 2, bigger than 1. Remember, this will be explained a little bit later, how we drop such terms which are not growing fast like the largest powers. But before that, one other example. Look at this. 1 over root here, third root, 3 and fourth power plus 1. The general term here is this, a sub n. So what I'm going to do, I'm going to drop this plus 1 here. This is what makes it different from P series. Just drop this. And the series becomes similar to 1 over third root 3 and fourth power, which I can write like that. Here this radical I can write third root of 3 times third root and fourth power, which will be third root of 3 times n power 4 thirds. And 1 over this radical I can put outside. It's in the denominator, so it goes out like that. It's a common factor for each term, and what is left is 1 over series 1 over n 4 thirds. This series is convergent. Convergent because it's a P series and P is 4 thirds, which is bigger than 1. So it is good when we do such work and some additional computations like this thing here. We do this on the side, not in front of the series. So here I did it below the series. So we're done also with this example. And now look at this one. I'm using now geometric series. 2 power n plus n cubed. I'm writing the general term. And here below we have 3n power plus 1. And changes from, let's say, 1 to infinity. For series, convergence or divergence is not influenced by the first several terms. You can drop several terms from the beginning. Convergence or divergence will not change. Same way when we work with sequences, if you drop a finite number of terms, the limit will not change. Now, how to deal with this series? On the top, we keep the term that grows fastest. And this is the exponential. So I shall drop n cubed. And below I shall drop this one. We know from the rule of L'Hopital that 2 power n grows faster compared to n cubed. So this is growing much faster, exponential grows faster. And after dropping these things, we find a similar series which is only 2 power n on top, 3 power n below. We can unite like that 2/3 power n. And this will be convergent because 2/3 is less than 1, between 0 and 1. So the initial series will be convergent. So if we simplify the series like I did and we come to a convergent series, our series is convergent. If we come to a divergent series, it will be divergent, like in our first example. One more with the geometric series. Look at this. Let's say I have 6 power n on top, and here below 5 power n plus 3. And let's say starting from 0 to infinity. Here, obviously, I can drop this 3. Drop this. And we come to similar series, which is 6 power n, 5 power n. it can be written 6/5 power n, and this series is divergent because the ratio 6/5 is bigger than 1. For the geometric series, we have to remember that when the ratio is bigger than 1, we have the divergence. Convergence only when it's less than 1. Okay, here look at this example. Series starting from 1 to infinity, n plus 1 on top, n cubed plus n below. Again, on top and bottom, we look at the terms which go fastest, and we drop all the others. So here I shall drop 1 on top and n below. So this will be similar to series just n on top, n cubed below, and this will be a convergent p-series. After reducing by n, we have a convergent p-series with p equals 2, bigger than 1. Okay, what is the theory that makes it possible to simplify like that and find the convergent or divergent series? The theory is this. We have a limit comparison test which goes like that. Limit if we have two series with positive terms, here one series with positive terms and another series with positive terms, and if the ratio a sub n over b sub n has a limit, so this is a sequence depending on it. If this has a limit, let's say a which is positive, so if this is true, then both series converge or diverge at the same time. So if the first series is convergent, the second is convergent. If the first series is divergent, the second is divergent, or the other way around. You can swap the positions of the two series, nothing will change. Because if this ratio approaches positive number, its reciprocal also approaches positive number. And how does it apply to our examples? Let's take the last example. Here we had on top n plus 1, n cubed plus 1 below. Let's say this is a sub n. When we removed the coefficient, the constant 1 from top and this smaller power n below, we compared to this series, 1 over n squared. So let's take this to be b sub n. If we take the ratio a sub n over b sub n, this will be n plus 1 over n cubed plus n, and dividing by 1 over n squared, we can multiply by the reciprocal. This will give you n plus 1 times n squared over n cubed plus n. And here we can study this ratio. We can simplify right here, or we can simplify later. Let's do it this way. I shall multiply, and this will be n cubed plus n squared, n cubed plus n. How to find limit of this sequence? Factor out n cubed and reduce, which is the same, divide top and bottom by n cubed. The ratio will become 1 plus 1 over n, 1 plus 1 over n squared. 1/n approaches 0, 1 over n squared approaches 0. There is a limit here, 1 plus 0, 1 plus 0. So the entire limit is 1, which is a positive number. So you see, because the second series, which is a p-series, convergent, the first one is convergent. the ratio approaches a positive number. So that's how we can apply our comparison test here, dropping the unnecessary terms which are smaller powers actually brings to a series where the ratio has a positive limit. There is another comparison test which compares directly two series. Let's just call it comparison test. Again, we're given two series with positive terms. Another series B sub n positive terms. And now suppose A sub n is less or equal to B sub n for all n. Then if the second series converges, then the first series converges. The terms of the second dominate the first and make it convergent also. But if the first is divergent, the second will be divergent. It will push from below the second one and make it go to infinity. So that's how this test works, just comparing the terms. And how can we apply it to our last example? Let's write again this series, n plus 1 on top, n cubed plus n below. So I shall take a sub n, the general term here, and I will find a bigger term with convergent series, reasoning like that. So first I can increase the numerator. Instead of 1 I can put n, like that. And below I can decrease the denominator, which makes things larger, so just keeping n cubed here. So if you increase the numerator, you get something bigger. Even let me make it in 2 steps to make it absolutely clear. So first we increase the numerator, we have this obvious inequality, and then I shall keep the numerator, this will be 2n now, and decrease the denominator, just dropping this n, and it will be n cubed. After reducing, this is 2 times 1 over n squared. And you can see, we can call this b sub n. A sub n is less or equal b sub n. B sub n is a term of one convergent p series. So our series convergent this way by this comparison test. So we can use either direct comparison, or we can use the limit comparison test. And with some experience, when we work with such series, you can see, you can get the good understanding what to cross out, which terms, and to drop to get one convergent series, or divergent series, to appropriate series for comparison. So doing more examples, that's how we get experience and better understanding of the topic. Oh, okay, this is enough. I think you are prepared enough to approach the homework. Goodbye.